Our entire history of progress is written in factories, from the first water wheel workshops to the sprawling automated plants of today. Every leap forward began with a new place to make things. Now we are running out of new places on Earth. The next great industrial leap will not happen on any continent. It will happen in the void above us. This video will show you exactly why the future of manufacturing and the next industrial revolution is being built in orbit. It is not about making satellites for space. It is about using the profound advantages of space itself, its weightlessness, its perfect emptiness, and its endless clean power to create materials and medicines we simply cannot forge here at home. This shift promises to reshape everything from the pills in your medicine cabinet to the computer in your pocket. What does a factory without gravity or limits even look like, and what impossible things will it build? The answers redefine what is possible. How do you think seeing our industry move into the sky will change our view of our own planet? Gravity is the silent architect of our world, shaping rivers, mountains, and even the flow of your morning coffee. Yet for the delicate art of building perfect materials, it is also our greatest adversary. Every factory on Earth is a battlefield against this constant, downward pull. It introduces chaos into processes that demand absolute order. When you try to grow a flawless crystal for a new medicine, gravity tugs heavier elements downward, creating layers of impurity and weakness. Attempting to mix two metals with different densities, like aluminum and lead, results in a frustrating separation, with the heavier metal sinking to the bottom in a process called sedimentation. Even the heat from a furnace creates turbulent currents called convection, which can leave microscopic stresses and bubbles trapped inside a cooling alloy, compromising its strength. These are not simple engineering challenges. They are fundamental physical limits, walls built by gravity itself that prevent us from creating materials of ultimate purity and perfection. Orbit offers a profound escape from this constraint. In the sustained microgravity of a spacecraft or station, the force that causes sedimentation and convection simply fades away. Without gravity's persistent tug, materials behave in ways that seem almost magical. Metals with wildly different densities can mix into entirely new, homogeneous alloys like a perfect, solid solution. Crystals can grow in every direction with symmetrical perfection, free from the distortions that gravity imposes. Imagine producing a semiconductor wafer with zero internal defects, or a pharmaceutical crystal with a purity that makes our current medicines look crude. This is not just an improvement, it is access to an entirely new design space for matter, a periodic table rearranged under new rules. By solving the gravity problem, we unlock the ability to engineer materials from the atom up in an environment where the laws of physics themselves seem to bend in our favor. But escaping gravity is only half the story. Our planet is also wrapped in a thick, protective blanket of air, an atmosphere that is essential for life but surprisingly hostile to precision manufacturing. Here on the ground, creating a true void is one of the most expensive and energy-intensive endeavors in modern industry. Laboratories and factories must employ massive, complex pumps that run for days, consuming enormous amounts of power just to suck away enough air molecules to simulate the emptiness of deep space. Even then, these artificial vacuums are fragile, constantly threatened by tiny leaks and contamination. In orbit, that perfect, profound emptiness is not a manufactured condition. It is the default state, a permanent and utterly free ultra-high vacuum that surrounds everything. This natural resource transforms impossible processes into routine operations. Take atomic layer deposition, a technique for coating surfaces with films just one atom thick. On Earth, stray molecules in the chamber can ruin the perfect layer. In space, the pristine vacuum guarantees flawless results every time. It allows for the handling of incredibly reactive materials without fear of contamination, enabling the creation of substances of a purity we can scarcely measure with terrestrial instruments. This is why the next generation of fiber optic cables, which could carry data with near zero loss, and the semiconductor wafers for computers 1,000 times more powerful than today's, will likely be born in this orbital emptiness. The vacuum of space is not just an empty backdrop, it is a foundational tool, as vital to this new industrial age as the steam engine was to the last. And remarkably, it is just one of several profound resources that space offers for free. While the vacuum offers pristine emptiness, it is the third resource that provides the sheer power needed to transform raw materials into finished products. Orbital sunlight is not filtered or fleeting. Above the atmosphere, solar radiation is nearly 50% more intense, and it shines 24 hours a day without the interruption of night or the scattering of clouds. This is not like a solar farm on Earth, which must contend with weather, seasons, and the daily cycle of darkness. In orbit, the sun is a constant, unblinking furnace, offering a torrent of clean energy that is simply impossible to replicate anywhere on our planet. For the heavy industry of the future, this changes everything. Processes that are prohibitively expensive or environmentally taxing on Earth become not just feasible but practical. Imagine using massive, lightweight mirrors to focus that endless sunlight into a beam of pure thermal energy, powerful enough to melt and refine asteroid metals in a floating forge, or to sinter raw lunar dust into solid structures through three-dimensional printing, all without burning a single gram of fossil fuel. This unending power supply eliminates the two greatest constraints of green manufacturing on Earth: intermittency and scale. It means a space-based factory can run its most energy-hungry processes continuously, driving down costs and enabling operations that would black out a city grid. The combination is transformative: a perfect industrial triad, weightlessness for perfect mixtures, a perfect vacuum for flawless structures, and perfect, endless power to make it all happen. This is the economic engine that makes the vision viable. But with the stage set and the tools assembled, a pressing question remains. What exactly will we build up there that is so valuable it justifies the journey? The promise of orbital manufacturing becomes crystal clear with a single, perfect sphere. Consider something as seemingly simple as a ball bearing, the tiny, polished orb inside nearly every machine that spins, from a dentist's drill to a giant wind turbine. On Earth, making one is a battle against physics. As molten metal cools into a solid ball, gravity pulls on the liquid mass, flattening it slightly at the poles like a miniature planet. This deformation, invisible to the eye, creates microscopic imperfections in its roundness. For the ultra-high precision machinery of modern medicine, aerospace, and computing, these tiny flaws are a major problem. They introduce vibration, increase friction, and cause wear, limiting performance and lifespan. It is a ceiling imposed by our home planet. In the stillness of microgravity, that ceiling vanishes. Without gravity's distorting pull, a blob of molten material is held together solely by its own surface tension, the same force that makes a water droplet form a sphere in mid-air. In orbit, that molten metal or ceramic will cool into a geometrically perfect sphere, every point on its surface equidistant from the center with atomic-level precision. Companies are already demonstrating this with materials like silicon carbide, creating spheres so flawless they roll with almost no friction. The value is staggering. Bearings made from these perfect orbs would make motors whisper quiet, allow scientific instruments to measure with unprecedented accuracy, and let machinery run for decades without maintenance. This one product, a perfect sphere, illustrates the entire value proposition of orbital manufacturing. It is not about making exotic things for space. It is about making essential things for Earth, but making them perfectly, in a way our gravity-bound factories never can. These perfect spheres point toward a revolution in machines, but the most profound impact of orbital manufacturing may be on us. It could rewrite the very process of healing. Inside every living cell are proteins, intricate molecular machines that govern health and disease. To understand how a disease works or to design a drug to stop it, scientists need a perfect three-dimensional blueprint of these proteins. They get this blueprint by coaxing proteins to form crystals, then shining X-rays through them. The problem is gravity. On Earth, as these delicate protein crystals grow, their own weight causes internal stresses and distortions. They become small, flawed, and riddled with imperfections, like a smudged fingerprint of the molecule. This makes the resulting blueprint fuzzy and incomplete, forcing researchers to spend years, sometimes decades, in a slow, frustrating process of trial and error to develop new medicines. In the stillness of microgravity, that friction disappears. Freed from the constant pull that distorts their growth, protein molecules can assemble into large, exquisitely ordered crystals of a quality impossible on Earth. These space-grown crystals provide X-ray maps of stunning clarity, revealing the exact shape of a disease-related protein, right down to the placement of individual atoms. This is not a marginal improvement. It is like switching from a blurred, ancient map to a high-resolution satellite image. For researchers targeting complex illnesses, from various cancers to Parkinson's disease, this clarity can shave years off the drug discovery process, leading to more effective treatments with fewer side effects, designed with precision we have only dreamed of. But the potential extends beyond molecules to entire organs. Here on Earth, attempts to bioprint living tissues, like a patch of heart muscle or a section of liver, face a familiar foe. Gravity collapses the delicate, intricate scaffolds before they can solidify, making it nearly impossible to create the complex, three-dimensional vascular networks that keep tissues alive. In orbit, bioinks containing human cells can be printed into shapes that hold their form, allowing the creation of sophisticated structures that mirror our own biology. This is not about printing a whole heart tomorrow, but about building the foundational layers of tissue that could one day lead to lab-grown organs for transplant, or incredibly accurate models for testing new drugs without risk to patients. The factory of the future, it seems, may not just build better ball bearings. It might help build a better, healthier human future. The same principle that can grow a perfect medicine crystal also allows us to invent entirely new forms of matter. On Earth, the periodic table is full of frustrating partnerships, elements that simply refuse to mix under the relentless pull of gravity. Think of oil and water, two liquids that will always separate into distinct layers. In the world of metals, similar immiscible pairs exist, like aluminum and lead. Their different densities cause the heavier metal to sink, creating a flawed, layered material rather than a true alloy. This is a fundamental limit of terrestrial chemistry, a wall that prevents us from blending the best properties of different substances into a single, superior material. Microgravity dissolves this wall. In that sustained quiet, without sedimentation to pull components apart, materials that would never combine on Earth can be stirred into a perfectly uniform mixture. This opens the door to a library of exotic alloys and composites with properties that sound like science fiction. Imagine a metal foam where gas bubbles are suspended evenly throughout a solid matrix. Created on Earth, the bubbles rise and escape, but in orbit, they stay locked in place, resulting in a material that is incredibly strong yet lighter than air, perfect for the next generation of aircraft or spacecraft frames. Or consider ZBLAN, a special type of glass made from a blend of metals that on Earth crystallizes as it cools, creating imperfections that scatter light. Formed in microgravity, it can solidify without those flaws, creating optical fibers so pure they could transmit data across continents with virtually no signal loss. These are not incremental upgrades, they are foundational breakthroughs, materials engineered from the atom up in an environment that defies our planetary rules. The implications ripple outward, promising computers that do not overheat, buildings that are both stronger and more resilient, and vehicles of all kinds that are far more efficient. Once we master the orbital recipe book for matter, the objects that shape our daily lives will be quietly, profoundly transformed. And this transformation raises a pivotal question, one of economics and scale. If the products are so valuable, how do we actually build an industry around them? Perhaps the most strategically critical industry on Earth is also the most fragile. The creation of a modern computer chip is a ballet of atomic-scale precision performed inside a fortress of unimaginable cleanliness. A single speck of dust, a human skin cell, is a boulder that can ruin millions of dollars worth of circuitry. This is why semiconductor fabrication plants are marvels of isolation, built on massive vibration-dampening foundations, with air filtered to levels thousands of times cleaner than a hospital operating room, and workers clad head to toe in protective suits. Yet, even these earthly cathedrals of purity fight a constant, losing battle against fundamental physics. The silicon wafers that become chips are large, thin disks, and like any thin material, they bend under their own weight, a phenomenon called wafer warping. As the scale of circuitry shrinks to just a few atoms across, this microscopic sag becomes a catastrophic distortion, throwing the incredibly precise patterning process out of alignment. We are approaching a wall not just of engineering, but of planetary condition. This is where the orbital factory presents not just an improvement, but an escape. Imagine the ultimate clean room, one where the environment is not manufactured at immense cost, but is a natural, permanent state. The inherent perfect vacuum of space eliminates airborne contamination entirely. There is no dust to filter because there is no air to carry it. More critically, the microgravity environment means a silicon wafer experiences no gravitational pull. It cannot sag or warp. It simply floats perfectly flat and stable in its processing chamber. This stability could allow for the creation of circuitry at scales we consider impossible on Earth, enabling not just smaller, more powerful chips, but entirely new three-dimensional architectures built in layers without the risk of distortion. The implications are profound. The very bedrock of our digital world, from smartphones to supercomputers, could be reborn in orbit, free from the terrestrial constraints that currently throttle its progress. It suggests a future where the most advanced technology on the planet is not made on the planet at all. This shift from earthly limitation to cosmic capability points toward a new economic logic, one where the high cost of reaching orbit is outweighed by the even higher value of what we can create once we are there. The greatest barrier to this vision has always been the staggering price of a ticket to orbit. For decades, launching anything into space was an endeavor reserved for governments and a handful of massive corporations, a cost measured in tens of thousands of dollars per single kilogram. It is a valid and powerful objection. Why would anyone build a factory in the most expensive industrial park in history? The answer lies in a fundamental shift in both economics and intent. The business case for orbital manufacturing does not rely on shipping heavy raw materials up or bulky finished goods back down. Its profit is in value, not volume. Think of it not as importing steel girders, but as flying in diamonds. The products that make economic sense are those with an extraordinarily high value-to-mass ratio. A single gram of a space-perfected pharmaceutical crystal capable of treating a disease with unmatched efficacy could be worth more than its weight in gold. A flawless semiconductor wafer, thinner than a human hair and packed with revolutionary circuitry, represents not a physical object, but the condensed potential of entire data centers. It is the difference between shipping a cargo container full of raw cocoa beans and a carefully packaged box of the world's finest Belgian chocolates. One is a commodity, the other is a luxury good defined by its perfection and the unique conditions of its creation. The return shipment from an orbital factory is not mass, it is concentrated innovation. This economic logic only strengthens as the final, most crucial barrier begins to crumble, the once prohibitive cost of the launch itself. The economics of space have been completely rewritten by a single, simple innovation, landing the rocket. For most of history, a launch vehicle was a masterpiece of engineering used exactly once, its multi-million-dollar components burning up in the atmosphere or sinking into the ocean. This made every trip to orbit a custom, exorbitant affair. The Space Shuttle, designed for partial reusability, still cost around $65,000 to lift a single kilogram into low Earth orbit. It was an expense that kept space the exclusive domain of national flags and deep public pockets. That paradigm has shattered. The rise of reusable rocketry, pioneered by companies like SpaceX with its Falcon 9, has turned the launch vehicle from a disposable fireworks display into a reliable semi-truck of the skies. By landing its first stage boosters back on drone ships or landing pads, the Falcon 9 has slashed the cost to orbit to just around $2,700 per kilogram. This is not a modest discount, it is a 25-fold reduction, a change so profound it redefines what is possible, and this is just the beginning. The next generation of fully reusable super heavy lift vehicles, like SpaceX's Starship, promises to push that cost down toward a few $100s per kilogram, a figure that begins to compete with the price of air freight for high-value goods. This order of magnitude collapse in launch expense is the essential infrastructure, the interstate highway system, for the orbital industrial age. It transforms the business case from a speculative gamble into a clear commercial calculation. When the cost of reaching the factory becomes a manageable line item rather than the entire budget, the immense value of what that factory can produce starts to dominate the spreadsheet. This launch revolution does not just make orbital manufacturing possible, it makes it inevitable, turning the final frontier into the next factory floor. For years, the only factory floor in orbit has been a magnificent, yet fundamentally limited, shared laboratory. The International Space Station is a triumph of global cooperation, a place of profound discovery, but it was never designed to be an industrial hub. Its modules are packed with 1,000 different experiments competing for power, crew time, and downlink bandwidth. Manufacturing there is a demonstration, a proof of concept squeezed into a locker-sized payload rack, operated by astronauts who have 100 other critical tasks. It is the equivalent of trying to start the automobile industry on a single, shared workbench in a busy community center. The experiments conducted there, from growing perfect protein crystals to mixing new materials, have proven the science beyond any doubt. They have shown us what is possible, but to turn that possibility into a true industry, we need a dedicated, scalable factory, not a shared science outpost. That factory is now under construction, not by governments but by commerce. A new constellation of private space stations is taking shape on the drawing boards and in manufacturing facilities right now, each designed from the ground up to be a commercial platform. Think of them not as successors to the International Space Station, but as something entirely new, the first industrial parks in space. Axiom Station plans to attach its initial modules directly to the International Space Station, later separating to become a free-flying complex focused on research and manufacturing, with spacious modules designed for ease of use and standardized interfaces. Voyager Space's Starlab is envisioned as a single module station, a compact but highly efficient platform meant to host continuous commercial operations. Perhaps the most ambitious vision is Orbital Reef, a partnership led by Blue Origin and Sierra Space, conceived as a mixed-use business park in low Earth orbit. Its design philosophy is telling. It speaks of open architecture, standardized utilities, and room to grow, the very language of terrestrial industrial development. These are not just habitats with a lab bench added. They are designed as infrastructure. They will offer something the International Space Station never could: dedicated manufacturing modules with robust, predictable power and thermal management systems. They plan for standardized docking ports and utility connections, allowing specialized production modules, like a furnace for alloy development or a bioreactor for tissue printing, to be plugged in and swapped out as needed, much like adding a new piece of equipment to an assembly line. Operations will be a blend of crew-tended and fully automated. Astronauts, or more accurately, specialist technicians, will be on hand to perform complex setups, maintenance, and quality checks, while the actual long-duration processing runs autonomously for weeks or months, monitored from Earth. This separation of roles is key. It turns the immense cost of human presence into a focused investment on high-value tasks, rather than a requirement for every single step. This evolution from a shared multinational laboratory to a suite of commercial facilities marks the critical transition from experiment to enterprise. The International Space Station was the prototype that de-risked the science. These new stations are the production models built to host the business. They provide the predictable, scalable, and specialized environment where companies can finally move in, set up their equipment, and begin the serious work of production. With the launch cost plummeting and the factory floor being built, the stage is almost fully set. But one final, intriguing question remains: where will the raw materials for this cosmic industry actually come from? The image of an astronaut in a bulky suit floating beside a whirring machine is a powerful symbol of space exploration, but it is not the future of orbital manufacturing. For an industry built on perfect precision and relentless efficiency, the human body is a liability. We require air, warmth, and protection from radiation, all of which add immense complexity and cost to a factory environment. The true workforce of these orbital facilities will be invisible, tireless, and perfectly suited to the void, advanced robotics and autonomous systems. Picture a module that is dark, cold, and silent, save for the precise hum of a robotic arm. It selects a raw material cartridge, feeds it into a three-dimensional printer whose nozzle glows with focused sunlight, and begins constructing a complex lattice structure layer by perfect layer. There are no coffee breaks, no shift changes, no need for life support. This is the concept of a lights-out factory, a facility that operates entirely on its own. The role of humans shifts from hands-on labor in a hazardous environment to remote supervision from the safety and comfort of Earth. Teams of engineers and technicians will monitor operations through high-fidelity data streams and video feeds, using advanced interfaces to make high-level decisions or troubleshoot issues. They might don virtual reality headsets to see through the eyes of a robotic inspector, examining a newly printed component from every angle without ever leaving the ground. Artificial intelligence will be the indispensable foreman, constantly analyzing sensor data to ensure every product meets its exacting specifications, adjusting parameters in real time to account for any subtle variance. This model solves the twin challenges of safety and scale. It removes people from direct danger while allowing production to run 24 hours a day, 7 days a week, unconstrained by human endurance. The orbital factory floor, then, is not a place for us to visit, but a system for us to command, a testament to our ability to extend our industrial will into the cosmos through the extension of our machines. With a workforce defined as a symphony of robotics and remote oversight, the final piece of the industrial puzzle falls into place, revealing a supply chain that stretches from the moon to the asteroid belt. But this grand vision faces a paradox. To build an industrial base in space, you need to launch enormous amounts of mass from Earth, which is precisely the expensive bottleneck we are trying to overcome. The elegant solution is to stop bringing almost everything with us and instead learn to live off the land, or in this case, the celestial land. This is the promise of in-situ resource utilization, a concept that transforms space from a barren destination into a stocked warehouse. The most valuable commodity waiting for us is not gold or platinum, but something far more mundane and infinitely more useful: water. Frozen into the permanently shadowed craters at the moon's poles and locked within countless asteroids are vast reserves of water ice. This is not just for drinking. Through a well-understood process called electrolysis, sunlight can be used to split that water into its basic components: hydrogen and oxygen, the very ingredients of the most common rocket propellants. Imagine a future depot at a stable point between the Earth and Moon, a cosmic gas station. A mining operation on the lunar surface harvests ice and processes it into fuel. Transport ships no longer need to carry all the propellant for their entire round trip from Earth. They launch from our planet with minimal fuel, refill their tanks at the orbital depot, and then have the energy to deliver their cargo anywhere in the inner solar system. The economic impact is transformative. By breaking our dependence on Earth for fuel, we effectively flatten the steepest part of the cost curve of space travel. Lifting a kilogram of water from the moon's weak gravity requires about 20 times less energy than lifting it from Earth's deep gravity well. This creates a powerful, self-reinforcing loop. Cheaper transport enables more mining and manufacturing infrastructure to be established, which in turn produces more fuel and materials, making transport even cheaper. It is the foundation of a true space-based economy. With this logistical chain in place, the most strategic locations for large-scale industry shift. Places like the lunar Lagrange points, stable gravitational parking spots where the pulls of Earth and Moon balance, become ideal. Here, massive, sun-drenched factories could operate, using lunar or asteroid-derived metals and space-harvested fuel to build everything from giant solar power satellites to the spacecraft for missions to Mars. The factory does not just exist in space, it is built from space, fueled by space, creating a circular economy that finally untethers human industry from its planetary cradle. While low Earth orbit is the perfect laboratory for perfecting materials, the true heavy industry of the cosmos will likely take shape much farther out, at a place of profound stillness. 22,000 miles above the equator lies a celestial highway called the Clark Belt, a ring of space where a satellite's orbital speed perfectly matches the rotation of the Earth. From the ground, anything parked here appears to hang motionless in the sky, a fixed star in the firmament. This unique characteristic, geostationary orbit, transforms it from a mere path into a permanent address, and that permanence is the foundation for its industrial future. Imagine a construction site that never moves relative to its customer. For an enterprise built on scale and continuity, this is an unparalleled advantage. The most compelling anchor tenant for this high-altitude industrial zone is one that solves a fundamental earthly need: endless clean power. Here, freed from the shadow of night and the filter of atmosphere, sunlight is not just constant, it is perfectly reliable. Visions for this future feature colossal solar power satellites, vast arrays kilometers across, assembled in the Clark Belt from materials mined and processed on the Moon or from asteroids. These would not be delicate panels, but rugged, simple structures designed for the harsh sun, converting photons into microwave or laser energy. That energy would then be beamed wirelessly with pinpoint accuracy to receiving stations on Earth, where it is converted back into electricity and fed directly into the global grid. This is not science fiction. The physics is sound and demonstrations have proven the concept. The scale, however, demands a space-based supply chain. This single application, beaming solar power from space, creates a massive, sustained demand for everything a space factory can produce: lightweight structural frames, advanced solar cells, and power transmission components. It becomes the economic engine that justifies the entire orbital manufacturing ecosystem, providing a steady, lucrative market that drives innovation and lowers costs for every other product. The Clark Belt would evolve from a communications corridor into a bustling industrial park, its fixed position allowing for the gradual, modular construction of immense structures, all powered by the eternal sun and serving the endless energy hunger of the world below. For centuries, the price of industrial progress has been written in our soil, our water, and our air. Our planet's surface has served as both our workshop and our dumping ground, a reality that is becoming increasingly difficult to sustain. This presents a profound and urgent question. Can we continue to advance without continuing to degrade our only home? Orbital manufacturing offers a radical but logical answer, not by abandoning industry, but by relocating its most demanding and polluting chapters off-world. Think of the immense energy required and the carbon emissions generated by a traditional blast furnace, melting ore into steel. Or consider the toxic chemical byproducts and heavy metal runoff from refining rare earth elements, essential for everything from electric car batteries to wind turbines. These processes are foundational to modern life, yet they carry a heavy environmental cost that we bear right here in our ecosystems and our climate. By moving these extreme industrial activities into space, we achieve a form of planetary stewardship through separation. In an orbital facility, the same metal refining process could be powered by that endless, clean solar flux, with its waste heat radiated safely into the void. More importantly, any toxic byproducts are not released into a flowing river or the open air. They are contained within the closed, manageable environment of the manufacturing module. They become not pollution, but a potential resource to be recycled or stored with precision, a far cry from the diffuse and damaging emissions of a terrestrial plant. This is not about running away from our problems, but about creating a new, cleaner ledger for heavy industry. By offloading the most energy-intensive and polluting segments of our supply chain to a place built for such extremes, we can focus our earthly efforts on lighter, greener, and more sustainable forms of production and assembly. It is a strategy of environmental triage, healing our planetary workshop by extending it into a realm where its impacts are no longer a threat to a living biosphere. The ultimate goal is a silent, profound dividend, a chance to let the Earth breathe while our ambition builds anew just overhead. This industrial shift will not just create new products, it will rewrite the rules of the global economy. The arrival of materials engineered to perfection in orbit will send shockwaves through terrestrial supply chains that have been stable for generations. Consider the market for advanced ceramics and specialty glass, essential for everything from laboratory equipment to the screens on your devices. If a company can produce a flawless, stronger version in space at a competitive price, entire mining, refining, and manufacturing sectors on Earth could face rapid obsolescence. This is creative destruction on a cosmic scale, where the factory of the future doesn't just compete with the factory of today, it makes its fundamental processes irrelevant. The old economic logic, based on controlling scarce mineral deposits or cheap labor, begins to erode. A new logic emerges, one that prizes access to the unique conditions of space and the intellectual property to harness them. This transition will be turbulent, displacing traditional industries while simultaneously conjuring markets for goods we can barely envision. We are not just talking about better ball bearings, but about active materials that can change shape or heal themselves, optical computers that process data with light instead of electricity, and alloys so lightweight and strong they make today's aerospace composites seem primitive. These are not incremental improvements. They are the foundation for entirely new categories of technology, creating industries that do not yet have a name. Who controls this high frontier, then, holds immense power. The geopolitical landscape of the 21st century could be defined not by borders on a map, but by orbits and Lagrange points. The nation or consortium that establishes a dominant presence in high orbit, with its permanent sunlight and stable platforms, gains a commanding lead in the next industrial era. This is not about planting flags, it is about controlling the means of production for the most advanced goods on Earth. It shifts strategic advantage from those with the largest oil reserves to those with the most innovative launch infrastructure and manufacturing platforms. Such a shift could alleviate tensions over dwindling terrestrial resources, but it also risks creating a new, stark divide between spacefaring and Earth-bound economies. The goal, however, is not a zero-sum competition in the stars. The most stable and prosperous outcome is a new economic paradigm, one built on abundance rather than scarcity. When the essential resources are sunlight, vacuum, and microgravity, which are available to anyone who can reach them, the playing field is theoretically open. Success will be determined by ingenuity, efficiency, and cooperation, rewarding those who can build the best systems, not just those who own the richest patch of ground. This could foster unprecedented international partnerships in space, even among rivals on Earth, because the cost and complexity of maintaining these industrial outposts will encourage shared infrastructure and standards. The ultimate promise is an economy unshackled from our planet's limits, where growth is no longer synonymous with extraction, but with the endless application of knowledge to the boundless resources of the cosmos. These immense possibilities rest on solving a new class of engineering puzzles, ones defined by the very environment that makes space so attractive. The first is a silent, invisible storm. Beyond the protective shield of Earth's atmosphere and magnetic field, orbital factories are bathed in a constant hail of cosmic radiation, high-energy particles from the sun and deep space. For delicate electronics and advanced robotics, this is a relentless, corrosive force. It can cause computer memory to flip bits randomly, degrade solar panel efficiency over time, and slowly embrittle materials. Building machines that can operate reliably for years, not just months, in this environment requires a radical rethinking of hardware. We cannot simply send up terrestrial robots. They must be radiation-hardened, with components designed from the start to tolerate this bombardment, or equipped with clever shielding strategies, perhaps using water or waste materials as protective barriers. This makes every bolt, every circuit board, and every sensor a custom piece of a cosmic survival suit for machinery. Then there is the puzzle of heat. On Earth, a hot motor cools by transferring its warmth to the surrounding air through convection, the same process that carries heat away from your skin. In the vacuum of space, there is no air to carry that heat away. Thermal management becomes a game of pure radiation. Excess heat must be deliberately pumped through fluid loops to large, finned radiators that glow faintly with infrared light, slowly casting the waste energy out into the void. This process is slow and meticulous, designing a factory module that can handle the intense heat from a solar furnace or a semiconductor processor without cooking its own internal components, is a ballet of precision engineering where every surface is part of a carefully calculated thermal equation. For any process involving biology, like cultivating tissue or perfecting pharmaceuticals, the challenge intensifies. A closed-loop life support system must be not just reliable but flawless. It must recycle air and water with near 100% efficiency, scrub out trace contaminants, and maintain perfect sterile conditions, all while operating autonomously for months at a time. A single seal failure or a bacterial bloom could doom an entire batch of priceless research. These are not minor tweaks to Earth-based systems. They are masterclasses in miniaturized, ultra-reliable environmental control. Finally, consider the simple act of construction. Assembling a large structure, like a solar power satellite kilometers across, cannot rely on spacewalking astronauts with wrenches. It demands a new generation of autonomous robotic assemblers, machines that can navigate, grasp, and join components in the confusing three-dimensional worksite of orbit, where there is no stable ground to push against. They must contend with Newton's third law, every action producing an equal and opposite reaction that could send them spinning away from their work. Solving this requires a combination of advanced machine vision, gentle but precise robotic grippers, and perhaps even the use of specialized caging or temporary structures to provide a stable frame of reference. These hurdles are formidable, yet they are not showstoppers. They are the defining engineering frontiers of our century. Each one represents a problem with a known set of physical laws, waiting for the brilliant, iterative work of engineers to solve. The companies and nations that crack these codes will not just reach orbit, they will build its foundation. But before we can build factories among the stars, we must first build a rulebook. The legal landscape for space is a frontier as vast and undefined as the physical one. Our current framework is built on treaties written in an age when space was a place for exploration, not industry. The cornerstone, the Outer Space Treaty of 1967, declares that no nation can claim sovereignty over celestial bodies. This is a beautiful ideal, but it leaves a critical question unanswered for the coming age. If a company cannot own a piece of the moon, who owns the metals it extracts from that piece? Who holds the title to a pharmaceutical crystal grown in a module owned by one nation, operated by a company from another, and using a process patented in a third? The question of ownership is just the first in a cascade of legal uncertainties. Liability is another gray void. If a robotic arm in orbit accidentally damages another company's module, or if a defective component manufactured in space causes a failure on Earth, which countries' courts have jurisdiction? There are no space police, no interstellar insurance adjusters. The existing liability convention assumes state responsibility, but private entities are now the primary actors. We need clear, modern rules that define fault and compensation, in an environment where a single accident could create a cloud of debris threatening every other asset in orbit. Safety standards are equally urgent. On Earth, factory inspections and building codes are enforced by national agencies. In orbit, who ensures that a manufacturing module's radiation shielding is adequate, or that its waste disposal protocols won't contaminate a shared orbital lane? A runaway reaction or a catastrophic failure in one facility could endanger an entire industrial park. This demands the creation of new international regulatory bodies, perhaps under the umbrella of the United Nations, with the authority to set and enforce baseline safety and environmental standards for commercial operations in space. This includes the critical concept of planetary protection, ensuring that our industrial activities do not biologically contaminate other worlds we may one day explore, or bring unknown hazards back to Earth. Finally, there is the matter of intellectual property. The process for creating a perfect alloy in microgravity could be a patent worth billions. But which patent office has authority? If an invention is made in a facility registered in Luxembourg by a team of remote engineers in India, using a robotic system designed in Japan, where does the innovation legally reside? Without clear international agreements on patent recognition and enforcement, the very incentive to innovate in space could be stifled by legal chaos. The challenge is monumental, requiring nations to set aside terrestrial rivalries and craft a new social contract for the high frontier, one that encourages innovation while ensuring safety, fairness, and responsibility. It is a test of our global maturity, proving that we can govern the unprecedented power we are about to wield. The grand architecture of this future is already being drafted in orbit today, not as blueprints but as working hardware. While the massive private stations are still on the drawing board, a fleet of smaller, specialized missions is proving the business case one perfect crystal at a time. Take Varda Space Industries. Their approach is beautifully direct, a small satellite that functions as a fully automated, miniature pharmaceutical factory. Once in orbit, it autonomously executes a crystallization process for a high-value drug compound, taking advantage of weeks of undisturbed microgravity. When the process is complete, the satellite packages the precious product into a heat-shielded capsule and sends it streaking back through the atmosphere for recovery. This is not an experiment, it is a production run, a quiet demonstration that the entire value chain, from launch to manufacturing to return, can be managed remotely and profitably. Alongside them, companies like Redwire Space are building the essential tools for this new industrial ecosystem. They have developed and operated advanced three-dimensional printers on the International Space Station for years, moving from simple plastic demonstrators to printing critical replacement parts and sophisticated ceramic tools in orbit. Their work extends to developing robotic arms capable of assembling large structures, like massive solar arrays, directly in space, proving that we can build things there that are too large or fragile to ever launch from Earth. These are the foundational technologies, the wrenches and lathes of the Orbital workshop. Government agencies are actively fueling this transition from science to commerce. NASA In-Space Production Applications Program, known as ISPA, functions as a crucial catalyst. It does not just fund experiments, it partners with private companies to help them develop specific, high-value products for terrestrial markets, from advanced optical fibers to novel therapeutics. The agency provides access to the space station's unique environment and expert guidance, effectively de-risking the path for businesses to establish their own future production lines. This partnership model is vital, bridging the gap between public sector exploration and private sector innovation. Each of these projects, whether a private company's daring capsule return or a government-backed crystal growth experiment, is a single, confident brick laid in the foundation of something monumental. They are moving us from asking if orbital manufacturing can work to demonstrating precisely how it will. The decade we are in right now is the proving ground. Through the 2020s, the focus is not on massive output, but on perfecting the machines and the business models. Companies like Varda are demonstrating the complete loop, from launch to manufacturing to return, proving that specific, high-value products can be made in orbit and sold profitably on Earth. The new commercial space stations like Axiom and Orbital Reef will come online during this period, transitioning from construction to active operation. Their primary role in these early years is to de-risk everything. They will host a bustling marketplace of experiments, refining three-dimensional printers for metals and ceramics, optimizing robotic assembly techniques, and running continuous production trials for those perfect spheres and flawless crystals. The goal by 2030 is clear: to move beyond single demonstration payloads and establish the first, reliable, and economically viable production lines for a handful of flagship products. This decade answers the question of feasibility with a resounding and commercial yes. The 2030s shift from proving the concept to building the industry. With the core technologies validated and initial products generating revenue, investment will flood into scaling up. We will see the launch of the first modules designed from the outset as dedicated, single-purpose factories. Imagine a module solely for semiconductor wafer fabrication, another as a high-temperature furnace for exotic alloys, and a third as a bioprinting hub for tissue engineering. These are not general-purpose labs, they are orbital versions of specialized plants, operating with high levels of automation. Crucially, this is also the decade where the supply chain begins to stretch beyond Earth. Early lunar missions will transition from exploration to resource prospecting and pilot processing. The first small-scale water ice extraction and electrolysis plants near the lunar poles will begin producing tens of kilograms, then hundreds of propellant. This fuel won't yet power the entire economy, but it will start to refill the tanks of transport shuttles at a nascent orbital depot, proving the logistics of in-situ resource utilization and beginning to lower the cost of operations farther from Earth. By the 2040s, the pieces start to fuse into a true industrial ecosystem. Lunar-derived propellant becomes a standard commodity, making travel between Earth, the Moon, and high-orbit routine and more affordable. This enables the construction of larger, more permanent infrastructure. We could see the first major industrial facilities at stable points like the Earth-Moon Lagrange points. These locations, with their constant sunlight and minimal orbital adjustments, become ideal sites for those colossal solar power satellite construction yards or large-scale refineries processing asteroid material. In high Earth orbit, the Clark Belt evolves from a corridor of communication satellites into a structured industrial zone, with standardized docking ports and shared utility services for multiple manufacturing facilities. On Earth, the impact becomes tangible. Space-manufactured products are no longer rare, million-dollar novelties, but critical components in the most advanced computers, the most effective medicines, and the most efficient renewable energy systems. They become embedded, often invisibly, in the backbone of the global economy. The horizon of 2050 and beyond is where the vision fully matures into a new economic paradigm. Orbital industrial parks operate with the routine hum of a terrestrial factory district. Their output's a staple of advanced technology. The dependency on Earth for raw materials diminishes significantly as a circular space-based economy takes hold. Metals mined from asteroids are refined in orbital furnaces powered by the sun, then used to build more factories or spacecraft on site. The beaming of clean solar power from space may become a measurable contributor to the global energy grid, a direct result of this off-world industrial capacity. This era redefines our relationship with our planet. Earth gradually transitions from a source of extracted raw materials and a site for heavy, polluting industry to a preserved biosphere focused on lighter manufacturing, advanced assembly, and most importantly, as the home for its civilization. The factory in the sky, once a fantastical concept, becomes the engine of a sustainable, post-scarcity future, allowing our planet to heal while our ambition builds a new world just overhead. This industrial leap will do more than just create new products in orbit. It will act as a powerful engine for innovation right here on Earth, generating solutions to problems we have not yet fully confronted. History offers us a clear blueprint for this phenomenon. The Apollo program, designed to land humans on the Moon, was not just about space exploration. The intense pressure to solve unprecedented challenges in computing, materials science, and life support spawned a wave of secondary inventions that reshaped our world. The integrated circuit found its first major customer in the Apollo guidance computer, catalyzing the entire digital revolution. Freeze-dried food, cordless power tools, and even the insulating materials in modern buildings are all Apollo-era spin-offs. The pursuit of orbital manufacturing promises a similar, perhaps even greater, wave of terrestrial benefits, born from the necessity of operating in the most demanding factory environment ever conceived. Consider the relentless drive for efficiency that space demands. Every gram launched from Earth carries a significant cost, and every cubic centimeter inside a station is precious real estate. This economic pressure will force a revolution in extreme miniaturization and multifunctional design. The robots that tend these orbital factories cannot be the large, bulky machines we use in terrestrial assembly plants. They must be incredibly compact, dexterous, and capable of performing multiple complex tasks with minimal human intervention. The advanced sensors, actuators, and artificial intelligence developed for these space-bound machines will inevitably filter down to Earth. Imagine surgical robots becoming so small and precise they can operate at a cellular level inside the human body, or disaster response bots that can navigate the rubble of a collapsed building with the grace of an insect. The need to do more with less in orbit will teach us how to build machines of astonishing capability and subtlety for use in our hospitals, farms, and cities. Then there is the ultimate test of sustainability, the closed-loop system. An orbital factory cannot simply vent waste or import new supplies of water and air from a nearby town. It must recycle everything with near-perfect efficiency to survive. The technology to achieve this, to purify water to an exceptional standard, to scrub carbon dioxide from the air and convert it back into breathable oxygen, and to reclaim valuable metals and chemicals from manufacturing waste, will be perfected out of sheer necessity. These are not just nice ideas for a greener Earth, they are absolute requirements for survival in space. Once mastered for orbital industry, these hyper-efficient closed-loop systems become a powerful toolkit for solving environmental challenges on our own planet. They could enable communities in arid regions to achieve true water independence, help us clean up polluted industrial sites, and move our entire global economy closer to a circular model where waste is merely a resource we have not yet reclaimed. Perhaps one of the most profound spin-offs will be in how we manage complex systems from a distance. Operating a factory that is 250 miles overhead requires a new paradigm of teleoperation and remote oversight. The latency in communications, though small, means direct, real-time joystick control is often impossible. Engineers will develop sophisticated interfaces where high-level commands are given, and onboard artificial intelligence executes the fine motor task. This requires blending virtual reality, haptic feedback, and predictive simulation in ways we are only beginning to explore. The systems created to guide a robotic arm in assembling a solar array in orbit are directly applicable to performing delicate repairs on deep-sea oil rigs, conducting precision mining in dangerous environments, or even performing complex medical procedures in remote field hospitals where a specialist cannot be physically present. The orbital factory becomes a high-fidelity proving ground for the future of remote work, one where expertise is delivered instantly across any distance, untethered from physical presence. In this way, the factory in the sky becomes a catalyst, a forcing function for human ingenuity. The extreme constraints of the environment will not just give us better products from space, they will compel us to invent better tools for life on Earth. The most lasting legacy of this next industrial revolution may not be the perfect ball bearing or the flawless crystal, but the unexpected technologies born from the struggle to create them, technologies that help us build a more resilient, efficient, and sustainable world right here at home. The ultimate promise of this cosmic industrial leap is not merely better products, but a fundamental shift in what we consider valuable. For all of human history, our economies have been defined by a single, crushing reality: scarcity. We fight over finite deposits of oil, rare earth metals, and fertile land because our planet only has so much to give. The resources of space, however, operate on a different scale entirely. The sunlight bathing a single asteroid belt is millions of times more intense than all the energy humanity uses in a year. The mineral wealth locked within a modest metallic asteroid could dwarf the entire global reserves of platinum or cobalt. The profound shift occurs when we combine this near-limitless raw material with the precision of orbital manufacturing. It suggests a future where the very things that drive geopolitical tension and economic inequality today could become astonishingly abundant. Consider the trajectory of a technology like computing. the cost of a single transistor has fallen from many dollars to a fraction of a penny over decades, a miracle of terrestrial miniaturization. Yet we are now hitting physical walls, the wafer warping and thermal issues that stem from our gravity-bound processes. Orbital semiconductor fabs could shatter those walls, enabling not just more powerful chips, but producing them in volumes that make today's output seem quaint. If the foundational element of our digital age, processing power, becomes as cheap and ubiquitous as sand, it unlocks possibilities we can barely fathom. Advanced artificial intelligence, personalized medicine driven by constant genomic analysis, and immersive virtual worlds could transition from luxury services to universal utilities. This logic extends powerfully to human health. The most effective medicines are often the most difficult to produce, requiring crystalline structures of impossible purity. Today, that difficulty translates directly into high cost and limited access. If orbital bioreactors can produce these perfect pharmaceutical crystals in continuous, automated batches, the economics of healing transform. A drug that costs hundreds of thousands of dollars per dose today could see its price fall by orders of magnitude. The goal is not just to create new treatments, but to democratize them, making the most advanced therapies accessible on a global scale. We move from a world where cutting-edge medicine is a scarce resource rationed by wealth, toward one where it is a manufactured commodity, as reliably produced as any other essential good. This is the incremental path toward a post-scarcity reality, not for everything, but for the most critical pillars of advanced civilization: energy, information, and health. It does not mean all wants are fulfilled, but that the basic building blocks of a dignified, modern life cease to be objects of fierce competition. When energy beamed from space becomes a major grid input, the cost of power could approach zero. When advanced materials are forged from asteroid ore in orbital furnaces, the price of building resilient infrastructure plummets. The result is an economy increasingly decoupled from extraction and depletion, and instead founded on knowledge and access. Our relationship with value itself would evolve, shifting from an obsession with owning scarce things to a focus on creating new ideas, experiences, and forms of art. The factory in the sky, then, is more than an industrial tool. It is a catalyst for a quieter, more profound revolution, one that slowly unshackles human potential from the ancient constraints of a single, fragile planet. A permanent factory in orbit would be the most profound shift in our night sky since the first artificial satellite. For 70 years, the points of light tracing the heavens have been messengers, spies, and scientific outposts, symbols of exploration and observation. A glowing industrial complex, visible to the naked eye as it catches the sun, would represent something entirely new, a place of work and creation. It transforms the cosmos from a distant frontier to be studied into a workshop to be inhabited. This simple, visible change carries a deep psychological weight. When we look up and see not just where we have been, but where we are building, it rewires our sense of place in the universe. We are no longer just creatures of the land looking out. We become a species actively extending its reach, stitching our industry into the fabric of space itself. That constant, silent reminder overhead could cultivate a cultural perspective shift as significant as the industrial one. It makes the idea of a multi-planetary civilization feel less like a dream and more like an ongoing project, a logical next chapter already in progress. This tangible expansion beyond our atmosphere fosters a powerful duality in how we view our home planet. On one hand, seeing our industrial activity successfully relocated to the heavens could reinforce a sense of Earth's uniqueness and fragility. If the dirty, demanding work of forging metals and processing chemicals can happen out there, it underscores that here is where life thrives. The planet transitions in our collective mind from a factory floor to a living heirloom, a garden to be tended with greater care precisely because we have found other places to do our heavy lifting. This could accelerate a global ethic of stewardship born not from limitation but from capability. We protect Earth not because we are trapped here, but because we have chosen to, because we have the means to preserve its beauty while meeting our needs elsewhere. Simultaneously, this off-world foothold encourages a radical lengthening of our cultural timelines. All of human civilization has operated on what we might call planetary time, constrained by the resources and cycles of a single world. The construction of infrastructure meant to last for centuries in orbit, and the planning of supply chains that stretch to the moon and asteroids forces us to think in generational terms. Projects are conceived not for a single political cycle or even a human lifetime, but for the benefit of a civilization that intends to endure across worlds. This long-now thinking could slowly permeate our approach to challenges back on Earth, from climate engineering to the preservation of knowledge. The factory in the sky, then, becomes more than a source of perfect products. It becomes a cultural compass, reorienting our gaze both outward to our growing domain and inward to the precious world we now see whole. Such a grand vision naturally invites sharp and necessary skepticism. One of the most powerful critiques centers on opportunity cost. With so many urgent challenges here on Earth, from climate adaptation to global health, is it morally or practically right to invest vast resources in building factories in space? This is a profound question of priorities. The counterpoint lies in recognizing that these are not mutually exclusive paths, but deeply interconnected ones. Historically, frontier industrialization has not drained resources from solving core problems, but has instead generated the very tools and wealth to address them more effectively. The technologies spun off from the space race, from satellite monitoring that lets us track deforestation and crop health to the advanced materials in water filtration systems, have become essential instruments in our terrestrial toolkit. The pursuit of orbital manufacturing, with its intense focus on closed-loop systems, hyper-efficient robotics, and clean energy, is likely to accelerate breakthroughs in sustainable living and remote medicine right here at home. It is not an escape from Earth's problems, but a high-stakes laboratory for developing the next generation of solutions. Another serious concern is the risk of turning the orbital lanes into an impassable junkyard. A catastrophic collision or a runaway fragmentation event could create a cloud of high-speed debris, rendering entire orbits unusable and trapping us on our planet. This danger, known as the Kessler syndrome, is a legitimate and critical engineering and regulatory challenge. It is not, however, an inevitable outcome. It is a problem of management, one we are already learning to solve. The new commercial stations and satellite constellations are being designed with end-of-life plans as a core requirement, incorporating propulsion for safe deorbiting or moving to graveyard orbits. Active debris removal missions are moving from concept to demonstration, with spacecraft testing nets, harpoons, and robotic arms to capture and dispose of defunct hardware. Building a sustainable orbital industry depends entirely on maintaining a clean and safe operating environment, creating a powerful economic incentive for the very companies operating there to champion and fund these cleanup technologies. The goal is not to conquer space and leave a mess, but to establish a careful, responsible stewardship from the very beginning. There is also a fear that the benefits of this cosmic industry will flow only to a privileged few, exacerbating global inequality. If the most advanced medicines, materials, and energy come from orbit, who controls them? This is perhaps the most crucial social question of the new space age. The architecture of access will determine its legacy. The optimistic and necessary counterpoint is that the foundational resources of this new economy, sunlight and microgravity, are not monopolizable in the way a terrestrial oil field or rare earth mine is. They are conditions, not deposits, The barrier is not ownership but the cost of entry. As launch costs continue to plummet and standardized factory modules become available for lease, the potential exists for a far more diverse set of nations, universities, and even consortia of smaller companies to participate. The model could shift from one of exclusive control to one of shared infrastructure, akin to how the Internet's backbone allows countless entities to build services upon it. The ultimate safeguard against a divisive space-based inequality is robust, forward-looking international law and trade agreements that prioritize broad access and benefit sharing, ensuring the dividends of this new frontier contribute to lifting prospects everywhere. Finally, there is the sheer audacity of the vision itself. It can feel like science fiction, a distraction by dreamers while practical problems mount. Yet every great industrial leap has seemed audacious before it became ordinary. To the farmers of the 18th century, the idea of a network of iron rails carrying steam-powered carriages across continents would have seemed utterly fantastical. The pioneers of the semiconductor industry were told that the market for computers would never exceed a handful of units for governments and large universities. The pattern is clear. Transformative industries are born from visions that challenge the apparent limits of their time. The skepticism is a healthy stress test, forcing clearer engineering and fairer governance. But history suggests that the most powerful driver of human progress is not just solving the problems we see, but building the capacity to solve problems we have not yet imagined. The factory in the sky is that next capacity, a tool not just for making things, but for expanding the very boundaries of what is possible for our species and our planet. We can recognize a true industrial revolution not by a single invention, but by a powerful convergence. History shows us a clear pattern. The first great leap was powered by steam, a new source of energy that unlocked mechanical work on an unprecedented scale. This energy found its home in a new locale, the centralized factory, which replaced scattered cottage industries. Later, the digital revolution introduced a new form of control, the programmable computer, which automated logic and information management within those factories. Each revolution required this triad: a new energy source, a new place of production, and a new system of control, all arriving together to create a discontinuity, a leap in what humanity could build. What we are now witnessing in orbit is not a collection of interesting experiments, but the precise reassembly of this revolutionary framework under a new sky. The new energy source is the relentless, unfiltered power of orbital sunlight, a torrent so constant it makes terrestrial solar power seem intermittent by comparison. This is our steam engine, but one that never needs coal and never rests. The new locale is the factory module in the quiet of space, whether attached to a private station or operating autonomously, a production site freed from the fundamental constraints of gravity and atmosphere. This is our centralized mill, but one that operates in 3 dimensions without a floor. The new system of control is the symphony of artificial intelligence and advanced robotics, capable of managing complex, precise manufacturing processes remotely and autonomously for months on end. This is our programmable logic controller, evolved to handle the physical world in a hostile environment where human hands cannot go. It is the convergence of these 3 factors: energy, locale, and control, in the unique environment of space that creates the conditions for a discontinuous leap. This is not merely an extension of our current industrial base into a higher orbit. It is the foundation of the next one, a system where the rules of production are rewritten by the physics of the void itself. The perfect sphere, the flawless crystal, the unimaginable alloy, these are not just products. They are the first artifacts of a new industrial age, proof that the revolution has already begun its quiet ascent. The convergence is now undeniable. A perfect vacuum, unlimited solar power, and the profound quiet of microgravity have always existed, but they remain distant curiosities, separated from our economy by the sheer expense of the journey. That final barrier is dissolving before our eyes. Reusable rockets are not just lowering a price, they are dismantling a wall. When the cost of reaching orbit falls from a king's ransom to a commercial freight charge, the economic equation flips entirely. The immense value of what can be created in that unique environment suddenly outweighs the cost of getting there. This is no longer a question of if, but of when and by whom. The next industrial revolution will unfold in the black silence above us, not because it is a simple or obvious step, but because it is the necessary one. Our civilization is pressing against planetary limits, not just of resources but of physical law. Gravity, atmosphere, and the day-night cycle are ceilings on the purity of our medicines, the strength of our materials, and the cleanliness of our energy. To transcend these ceilings, we must move the workshop to a place where those limits do not apply. This shift represents more than a new market or a novel technology. It is a fundamental reorientation of human enterprise, a deliberate step into a broader arena. For the first time, industry is leaving its planetary cradle. The century ahead will be defined by this great offloading, where we gradually relocate the most demanding and transformative acts of creation to a realm built for them. Our role is to witness and to shape this transition. The companies building the first private stations, the missions returning those first vials of space-perfected crystals, the engineers solving the puzzle of robotic assembly in a vacuum, they are writing the first draft of this new chapter right now. To follow their progress is to watch the blueprint of the future being drawn in real time, a future not of scarcity, but of cosmic abundance, forged in the quiet factories between the stars.